Good afternoon, everyone. My name is Ruofeng Feng from University of Manchester. Today, I'd like to talk about my study on developing SPH for geotechnical applications, ground flows and rainfall-induced landslides. So for today's talk, I'd like firstly introduce the background of this topic. This is followed by the single-phase SPH formulations for dry cells, which would be the first part of this talk. Here I will show you the results of element test and the Granular form. After that, I will introduce a two-phase SPH formulation for unsaturated soil, in which I will present the results of one-dimensional infiltration test and rainfall-induced landslides. And finally, I will draw some conclusion and present you some future works. To start today's talk, I would like to show you some recent example of geohazards. The first case is the tailings dam failure, which occurs in Brazil in 2019. You can see the failure process is quite catastrophic, involving massive sliding mass. The traveling distance is significant, and it was reported at least 200 people died due to this disaster. At the bottom, there is a case of landslides induced by heavy rain occurs in Japan. As we can see, the muddy flow heavily destroys the structure and buildings at the downslope region. After had these disasters, the question put on our geotechnical engineers are how could we properly predict the onset of this instability, and how could we evaluate the risks and the consequence of such disasters? So the computational challenge we are facing is that we had a complex physics. So it's a multi-phase problem because it's soil, it will have water and soil skeleton or air. And soil itself will display non-linear behavior. And at a post-failure stage, it will involve large deformation and free surface flow. However, common practice in geotechnical engineering is still heavily relying on the mesh-based method. So such as FEM. Such mesh-based method has a problem, which is mesh distortion when it comes to large deformation, as we can see from the left figure. So this kind of problem motivates us to investigate a new numerical tools to bridge the prediction of onset of instability and the consequence of the subsequent motion of this sliding mass. So it comes to the first part of this talk, single-phase SPH formulation for dry cells. Here we will address the nonlinear material behavior and large deformation. So for the governing equation, the conservation of the mass and momentum is quite similar to what we had in fluid dynamics, because we are both based on continuum mechanics. So the thing need to note is that we use stress rather than pressure in the momentum equation. Also, I include artificial viscous term in order to stabilize the simulation, also to reduce numerical oscillations in a velocity profile. So the main difference is that for the constitutive relations, we use something more complex. So you may know that in some study, they may use the fluid models, such as non-linear model, to simulate landslides. But here we would like to take advantage of the knowledge of soil mechanics. So here we use a elastic plastic constitutive model to simulate the soil behavior. So here we have a stress rate equation, which is to relate the stress rate to strain rate. And for the elastic plastic theory, we need to define the yield function. Here is Draper pressure yield criterion, and also the plastic potential function to determine the direction of the plastic deformation. Here also consider the strain softening. So there is a strength parameter related to the plastic strain. So when it comes to large deformation, the strength parameter will reduce in order to capture the strain softening. To update the stress, we have a procedure which we called elastic predictor and a plastic corrector. So for stress point A, we will assume a elastic condition to predict its stress to point B. If point B exceeds the yield surface, we have a plastic corrector to return this stress back to the yield surface in order to satisfy the yield criterion and also the plastic flow rules in the theory of elastic plastic model. So here we will have an iterative algorithm to update stress. So a common problem of SPH is collotraction of particle near the boundary. Here we construct layers of particle in order to complete close support of the particle near the boundary. And also in computational geomechanics, we also need the free slip and the no-slip boundary condition. So here we adopt the building block of MDBC by English in 2021. We use the fixed ghost particle technique to evaluate the field variable of boundary particles. So the no-slip, free-slip boundary condition is quite similar to what we had in MDBC. The main difference is that we extrapolate the stress rather than density. And also, since we do not have a DBC, when the renormalization matrix is EU conditioned, it reduces to zeroth order interpolation. And in order to improve the accuracy, we assume a geostatic condition near the boundary to extrapolate the stress point from the loads to the boundary particles. Another problem for the geotechnical application of SPH is that there is nucleus in the stress field. So as we can see from the figure here, the two-dimensional granular column collapse. So inspired by the density diffusion turn in fluid dynamics, which achieved quite success in prediction pressure, we consider diffusion process in stress updating. So expression of the diffusion turn is quite similar to density diffusion turn in fluid dynamics. But what we need to consider is the diffusion operator. The diffusion operator has a quantity of the has a dimension of the quantity to be diffused. So here we express it in using stress and modify it from Potax and in 2019 for smoothing of stress. So for people may interested in our study, you can refer to our recent publication for more details. And the proposed scheme is implemented in an open source SPH solver geophysics. So in the following, I will present you the test cases, and the first one is the element test. This one is to ensure the implementation of the constitutive model in the SPH. So as you can see from the figure, there is a soil specimen in the center, which is enclosed by the boundary area. We will send the prescribed velocity field to the boundary particles to generate a pure sharing deformation. Also, we'll measure the stress and strain in the center of soil specimen, and here are the results. As we can see that the shear stress and shear strain are in close agreement with the single element solution, and as we increase the softening coefficient, we can obviously observe this strain softening due to the large deformation. And also the velocity profile is maintained very well for the simulation, in the simulation. The next case is we apply our model to simulate the granular fall and compare it with the experiment data by Ruofeng in 2017. And here we investigate two sets of initial aspect ratio, and you can see the image of the experiment. So, because they use non-cohesive material, so in this simulation, we do not consider the cohesion. So here are the results. As we can see, due to the use of diffusion algorithm, we have quite smooth stress profile. And in order to measure the difference of the first surface profile between numerical results and the experimental results, we have a parameter here for the comparison. So here are the results. The first one, there are 6 time instants. You can see at the initial stage, there are some sort of gaps between the limit simulation and the free surface profile, but soon after, or in the following time instance, we get quite good agreement with experimental data. And if we take a look at the final instant, there is an undisturbed region at the top left. While if we increase the aspect ratio, we could see we don't have this undisturbed region. It's a kind of hole failure. So we capture the failure mechanism of granular fall under different aspect ratio. And also we achieve a great agreement with experimental data in this case, except for some small gaps at the initial stage, which we think it could be the limitation of our constitutive model, in which we do not consider the volume expansion here. So at last, for this part, I apply the model to simulate a quite challenging topic, which is retrogressive solvent failure. As we can see from the left-hand side figure, there are the typical retrogressive solvent failure. You can see there are multiple failures involved, and the retrogressive solvent failure is mostly found in sensitive clay, which displays strain softening, and that's a reason why it can change from initially very stiff state to a fluid-like state. This poses challenging for traditional mesh-based method because it involves quite large deformation and multiple failures. So here we have our results. You can see that initially, and the failure occurs at the slope toe and then propagate into the inner slope. So we capture these multiple failures, and also we have the smooth stress profile due to the use of diffusion. So let's move on to the second part, which is two-phase SPH formulation for unsaturated soil. Here we will address the multiple phases and hydraulic condition. As we will see in the left-hand figure, for a natural slope, it is subject to the environment condition, such as fluctuation in the groundwater flow or climate conditions, such as evaporation, rainfall, infiltration, or the influence of a plant. Also, for soil itself, it's a multi-phase mixture. So that's the issue we would like to simulate. So how to simulate unsaturated soil? If we take a look at this particle, unsaturated soil is a multi-phase mixture involving soil phase, water phase, and air phase. Here we simplify this problem to two-phase problem, so involving water phase and soil phase. So we do not involve air density, and we consider the air pressure as a constant. The unsaturated conditions are taken into account by considering the evaluation of the water count and the presence of capillary pressure. So for the simulation of the multi-phase problem, we just use one single set of particles. So it's not like one set of particles for one phase. So for our case, a single SPH particle will contain the information for both soil phase and water phase, and the contribution of each phase to the whole mixture will be evaluated using the concept of volume fraction. So here are the governing equation for unsaturated soil. So for the mass balance equation, for the governing equation, you may be familiar with the equation of fluid dynamics. And here are the equation for the soil phase in our simulation. And the difference is that the material derivative is attached to the soil phase. And we do not involve density because we assume the soil grain is incompressible, but the solid skeleton is compressible. So we involve the volume fraction of soil, or we can consider it as porosity. And here we use stress, not pressure. And for the water phase, we will have this equation, which is quite similar to the mass balance equation of fluid. But here we have an extra term, which is called a storage term, which is important for unsaturated soil. And here we have the seepage discharge rather than the fluid velocity. And here are the Darcy's law. The combination of the two equations is a well-known Richards equation for unsaturated seepage flow. So after discretization, we have our SPH equation. This is combined with hydraulic model, mechanical model to close the governing equations. So how to simulate the rainfall infiltration? So here we consider a slope subject to the rainfall. Here we do not really simulate the rainfall process. So we apply certain free surface boundary condition to simulate the rainfall event. So as we can see here, we apply infiltration boundary on the free surface for the water inflow, and for the impermeable bedrock here, we lead solid wall boundary condition for no slip and free slip in both soil and the water phase. So for the infiltration boundary condition, we could consider to use the lateral boundary condition because zero pressure is implicitly satisfied along the free surface. It zero pressure in the survey of unsaturated soil means that it's fully saturated condition. So it will enable the water infiltration. But it has an advantage because it do not require extra computational efforts, but it do have limitation because we cannot investigate the influence of rainfall intensity and the rainfall duration. So that's the reason why we prefer to use this essential boundary condition. We directly impose a prescribed infiltration rate on free surface particles. So for this, we would firstly search the free surface particle and apply a prescribed infiltration rate on those particles. And for the wall boundary condition, the established boundary condition for granular flow using MDBC is extended for the copper problem. So we have the low slip, free slip boundary condition, which is quite similar, and we extrapolate both stress and density. So you can refer to our recent publication for more details. So here are the test cases. First is infiltration test. This is to test the boundary condition and also the unsaturated seepage framework.
Here 5 minutes.
Yep. Here we have unsaturated soil initially with selective 5 kilopascal, and we apply a zero pressure boundary condition at the top and the impermeable boundary at the bottom. And to enable one-dimensional water flow, we have a periodic boundary condition at the sides. So at the right-hand side, the blue line stands for SPH results, and the red line denotes an analytical solution. So if we run simulation, we can see we get quite close to the analytic solution. So finally, we apply the model to simulate the rainfall-induced landslide experiments. So at the top left, we have the photo of the experiment. There are a slope building on the steel framework, and the rainfall intensity is given, so which is 100 millimeter per hour. the rainfall duration is greater than 2.5 hours. So it's a very long-term simulation, which is quite challenging in our case. So if we run simulation, we can see as we start, there are water flow from the flat surface, and when the wetting front reaches the impermeable bedrock, there is accumulation of water. And further go, at some point, the failure occurs. So the wetting process is clearly reproduced without any numerical noise. So here we compare our results with experimental data. At the top is a phreatic surface, and which is a water table. We have a close agreement with experimental data, and more importantly, at the bottom, we correctly predict the location of the failure surface and the shape of the sliding surface, which is very important to prevent disaster. So both those predictions are in good agreement with experimental measurements. So for conclusion, we have developed SPH for geotechnical problems, including single-phase ground floor and two-phase landslide. Here we'll adopt classical soil constitutive model to better reproduce soil behavior, including plastic deformation and strain softening behavior. So we investigate boundary condition and numerical diffusion to improve the accuracy and stability of the simulation, and the methodology allow us to investigate the entire failure process. So for future work, we would like to broaden our application to general geotechnical problem. For example, the two-dimensional dam seepage case at the bottom. So there are two different shapes of dam and sustain a certain water level, and the preliminary results show good agreement with FEM solution by Pedroso in 2015. And also we are interested in to extend the new method to three-dimensional for real engineering applications. So thanks for your attention, and if you have any questions. That's it.
Thank you, Ruofeng. So I'll start with kind of a trivial question. Right at the beginning, when you showed your discrete SPH equations, yeah, probably this one. Mm-hmm. So for the strain rate, do you do anything special, or is it similar to the so instead of divergence of velocity, you calculate the gradient of velocity, or yeah, is there anything special to calculate the strain rate?
Sorry, I did not present the calculation of strain rate, but it's similar to the mass balance equation. So we calculate the velocity gradient. So we use the operator similar to this one. So it's standard SPH formulation for the strain rate.
Yeah. Okay. Right, let's see. Yeah, I don't see any. Yeah, Stephen.
Oh, sorry, I put my hand down and then put it up and then put it down again and then put it up again. I pressed the button too many times. What kind of computational overhead or computational sort of implication is there to this model? I'm just wondering what scale of simulation can you feasibly get to? Because I appreciate, you know, with the scouring model and so on and so forth, that it's probably more than sort of a typical SPH simulation, just handling fluid.
Yeah, so basically in current stage, we we do not really consider the computational efficiency. So I take a simple example. For example, for the simulation of the 2.5 hours physical time simulation, the case here, I would takes around 3 days for this 2.5 hours simulation for particle, maybe thousands particles. So yeah, we do not really improve the computational efficiency, but yes, we do. We are considered to move the code to maybe a GPU acceleration to improve the computational efficiency. That would be the aims for my future work for sure. Yeah.
Okay. Yeah. Thanks.
I just have one question on the two-phase simulation. Yeah, it's not really my my area of expertise, but so you have two sets of, or well, you have 4 equations, but you have a set of equations for soil and for the liquid. Are they coupled, or how are they solved? How do you integrate those two equations, and is there any coupling between them?
Yeah. So basically, we have 4 equations, 2 for soil phase and 2 for water phase. We solve this equation in the single SPH particle. So for the governing equation, the material derivative is attached to the soil phase. So we consider the soil as the movement will be the soil. So we solve the 4 equation in the single SPH particle. So the idea is that we do not use one set of particle for water phase, one set of particle with soil phase. Is that we are more interested in the soil behavior, soil movement. So we do not solve the water outside the soil. So we just consider the movement of soil. So here we solve 4 equations in the single SPH particle. So also it can improve the computational efficiency because we have less particle involved. So that's the main idea for this one. I don't know if it answers your question.
Okay, thank you. I don't see any further questions. So thank you, Ruofeng, for a very interesting talk, and thanks to the other 2 speakers as well. So we can close the first session here. So we'll have a 15-minute break now, and we'll start again.